Here is part 2 of the rotation function worksheet. In section B, it says to identify the transformation used to create the images below and write congruency statements for the corresponding sides of the figures. For reflections, identify the line of reflection. For rotations, identify the centering angle of rotation. Okay, so looking at these two triangles here, we could call one of them our preimage, and let's say PMT is our preimage, and XYZ is our image. And what the question is asking is, how can we do a single transformation that will take PMT and place it in the position of XYZ, or in other words, map it onto XYZ? And there's only a few transformations that we know of. We know reflections, rotations, translations. So let's go ahead and try and figure out what transformation would take this to this by the process of elimination. So you might say, maybe we could do um, a translation, right? But let's sort of think about that, right? If we take PMT and we try to translate it down to XYZ, you very quickly see that this is not going to work, right? So a translation's off the table. And then you might say, okay, well, what about a reflection? Well, um, let's say that we were to reflect PMT across a vertical line, right? It would look something like that, right? Let's say we have a vertical line. We reflected PMT across that vertical line to get this purple triangle. Well, that clearly doesn't work, right? But then you could reflect this purple triangle horizontally, and then we would get XYZ. But of course, that would be two transformations, and we're looking just for the one. So if it's not a translation and it's not a reflection, then it's very likely a rotation, right? And we can kind of see that that makes sense. This sort of looks like it's rotated about a point, somewhere around in this area. Now, to find the center of rotation, which is what this part wants, what we're going to need to do is we're going to need to make um, a line segment connecting corresponding points. Find the perpendicular bisector, and then do that again for another set of corresponding points. And where those bisectors meet is the center of rotation, right? So in this case, let's go ahead and see what that looks like in practice. I'm going to connect X and M. Well, I'm going to try and connect X and M with a line segment. And then I'm going to draw the perpendicular bisector to that. So for that, you're going to need a compass. And you're going to need to make your arcs. Bang, and boom. We got our arcs. So now we can connect that. I'm going to make our perpendicular bisectors purple. And hopefully straight as well. That would be a goal of mine. Okay, there we go. So there's our first perpendicular bisector. And now, so we want to do this process again for another two corresponding points, or at least points that we believe are corresponding. And where these two bisectors meet is going to be our center of rotation. So let's go ahead and do that. Let's connect Z and T, or look to me to be corresponding points. Hopefully they look that way to you as well. And then we're going to make the perpendicular bisector to that. And here I'll make my arcs orange. And of course, I did not draw my arc far enough, so I got to go back. Okay. And now I'm going to connect those intersections with a line segment. Right. And so we see that this purple bisector and this purple bisector intersect right over here. And that just so happens to also be the intersection of the line segment connecting our corresponding points, which is just a coincidence. It's not always going to be the case. Um, that all those intersections are going to coincide. Um, but in any case, let's go ahead and mark our center point, the black dot, and we will call that point E for the center of rotation. So to confirm that this is a rotation, you would have to connect Y and P and make sure that the perpendicular bisector is also going through E. And that would be the way to confirm that these are in fact a rotation of each other. But in this case, I'll just go ahead and tell you that this is a rotation. um, and so let's go ahead and erase some of these guidelines so that we can find what our angle of rotation is. So looking at this angle here, right, M was rotated, let's say in this direction, to become X, right? And that angle is making a straight line. And so we know that when we have a straight line like that, the angle is 180 degrees, right? So here we can put that this angle is 180 degrees. And that should be pretty obvious to you, but if it's not, you could have also used a protractor and placed it down and confirm that that is 180 degrees. If you start from here and flip our numbers, it's rotated 180. But a straight line will always be a 180 degree angle. So here we'll put that this shape was rotated. And now we have our center of rotation. We have our angle of rotation. And the last thing that the question that wants us to do is to write congruency statements. So in order to do that, we need to think about which sides are the rotations of their original selves, right? So MT here, MT should be congruent to um, the side that is its rotation, right? So MT, if this shape is rotated, would become XZ. And so MT is congruent to XZ, right? And hopefully I could get that underneath the bar right there. Yeah, so MT is right there is congruent to XZ, which means MT is the same size and shape as XZ. And we know that because these are rotations of each other, and rotations preserve congruency. And so that's one statement, but because this is a triangle, we have three statements because we have three sides, right? So let's go ahead and make a couple more of these so I don't have to be looking up the symbols each time. And we'll write the remaining congruency statements. And so we could say that PT, likewise, and you kind of have to envision in your head which side is the rotated side of PT. And in this case, because PT is on the outside, and ZY is also on the outside, when this rotates, it stays on the outside. ZY should be um, its counterpart. And those two sides are congruent. And lastly, by process of elimination, PM is congruent to XY. Those are the same size and shape. And so right there, that's the answer for question 1. And so now for question 2, we can look at this and say that there's a couple of possible transformations. I mean, it's clearly not a translation. But you might be thinking, maybe it's a rotation and, maybe it's a reflection. And in actual fact, it's both. It can be both of those. And if you were to try and find the center of rotation here and connect, what you believe to be corresponding points, so YA and then XM, and then you found the perpendicular bisector for those. So, the perpendicular bisector would look something like this, and you typically use a compass, but in this case, we'll just kind of sketch it in because I'm just want to show you, uh, where that center of rotation might be, roughly. We'd find that the center of rotation is, and this is, we'd find that the center of rotation is going to be somewhere out here, right? And so if you were to do this and you were to try and find the center of rotation, you'd find that the center of rotation is right there, and this shape was rotated about that point. And so that's one way of getting XYZ onto AFW, right? You could say it's a rotation, you can follow that whole process. And if you do that, I'd mark it right. But you could also say that this is potentially a reflection, right? And so that's the route that we're going to take, right? We're going to say that this is a reflection. And if we want to find the line of reflection of two shapes, the way to do that is to connect two corresponding points with the line segment and find the perpendicular bisector to that. And that would be our line of reflection, right? And so we have a ton of practice finding the perpendicular bisector, but let's just do it again just for, practice sake. Connect Z and F with a line segment, and then we'll use a compass to draw our arcs so we can get that perpendicular bisector precisely. Okay, so we're going to swing our arc here, and let's make that a little smaller here because, all right. Swing our arc here, and then finally we go to the other side. We make our arcs over there. And we have what should be our line of reflection, right? XYZ was reflected across this line to be A of W. In order to confirm that this is in fact a reflection, you'd have to measure the distance from X to this line and make sure that that distance is the same as the line as A to the line, right? Because 2 points that are reflections of each other should be the same distance to the line of reflection. And then you'd also have to confirm that Y is the same distance to that line of reflection as W is. Okay, but we're not going to do that here. It's just suffice to say that this is a reflection and that if you were to measure those out, they would be the same. And I will confirm that for you. Um, so here we have our line reflection, and we can say that this is a reflection. And now we go off to write our congruency statements. So let me go ahead and copy these over here so that we can reuse those symbols. And we'll begin the process of writing our congruency statements. And so clearly the side XY is the reflection of AW. And so we can say that those two sides are congruent. Right? But what about YZ? Well, you look at YZ and you look at the points, right? The reflection of Y is clearly W and the reflection of Z is clearly F. And so if those 2 points are reflections of each other, then the side between them should also be a reflection of the side between the corresponding points, right? So YZ is clearly a reflection of FW. So we can say that YZ is congruent to FW because they are reflections of each other. Okay, and then by process of elimination, the only remaining ones are XZ. And so XZ should be a reflection of AF. And so that right there are all the congruency statements that we can deduce from the fact that XYZ is a reflection of AFW. Now, it might be the case that YZ is also the same size and shape as AF, and those two are congruent. But we can't make that claim just off of the knowledge that this is a reflection, right? We'd have to measure YZ and measure AF in order to say that they are congruent. But in this case, that's not the goal of this practice. The goal of this is to make a congruency statement based off the knowledge that this is a reflection. Okay, so this would be all the congruency statements that we could say based off of that knowledge. All right, so going to part D. Part D says to draw and describe the sequence of isometries which show that the two figures in each pair are congruent. So the first thing we need to know is, what does isometry mean? And I already have it up here for you, right? Iso means same. And metry you can kind of think as meaning geometry, and so you could say that this means same geometry. And what that means is, and what I mean by that is that isometry is another word for rigid motion transformations, translations, reflections, rotations. And all those transformations preserve congruency, right? The shape that you transform is the same size and shape after it's been transformed, right? So you would say that it has the same geometry. And so that's why you would say that isometry is another name for the rigid motion transformations, translations, reflections, rotations. So here what the question is asking us is to state what kind of transformations took our pre-images, which are the bold lines, to our images. And it could be a combination of two or three of the transformation of the rigid motion transformations or isometries, which are translations, reflections, rotations. So let's see. What kind of transformations do we think took A, B, C, D onto our image over here? Well, you might be looking at this and you might say, well, that looks to me like a rotation. And so let's sort of think about that, right? Let's see. If we were to rotate A, B, C, D in this direction, what would that look like? Well, we can kind of sketch it in. Say it should probably look like something like this, right? And if we were to continue rotating this shape about C, you can very well see that it's not going to go into the position that A, B, C, D is in, right? Um, but once we get into this position, you could see that, maybe we could reflect it across the line and get A, B, C, D. And in fact, that's exactly what we can do. We can draw our line of reflection. And we can label that N. And just as well, we can label our shape over here. And we'll label that FEGH. And so that FEGH, when reflected across line N, gives us A prime, B prime, C prime, D prime. So to describe this rotation that happened here, we're going to write rotated. And actually, we should probably measure the degree of the rotation. And so in order to do that, if you imagine C as the center point, D was rotated from here over here in a circular path. And so we can measure the angle from this line segment to this line segment using the protractor. So grab your protractor, place the center of it at the center of rotation C. And this is our 0-degree line. So we're going up 20, 40, 60. We can see that it was rotated about 140 degrees, right? And in this direction, which is counterclockwise, which is positive, right? So we'll say rotated 180 degrees. And let me get the symbol for degree. About point C. Okay. And then after it was rotated, we reflected across line N. Okay. So then that would be sufficient to describe how we went from here, from A, B, C, D to A prime, C prime, D prime, B prime. And that would be a complete answer. However, you could also write this information in function notation. So you could write, for example, R for rotate, and we rotated about point C, 180 degrees in the positive direction. And our input shape was A, B, C, D. And our output was the shape that we labeled F, E, G, H. And then for the reflection function, we can write reflected, R for reflected, subscript N for our line of reflection that we labeled N. And our input points were the FGH shape. And our output was A prime, B prime, C prime, D prime. All right, so two ways to write this, to describe this transformation or sequence of transformations rather. You can either put it in, describe it in words, or you can describe it with the function notation. And only one of these you have to do for this assignment. Okay, so looking at question number 2, we have two shapes that are separated by some distance. Whenever this is the case, I feel that it is easiest to take, for example, DEF and place it in the position of DEF by starting with a translation. So whenever you have two shapes that are separated, I would always start with a translation that puts one point on top of another. So here I want to put this shape so that F and F prime are sitting on top of each other. And to do that, we can do a translation. So I'll grab a line segment, and we're going to go ahead and translate this shape in the distance and direction of F to F prime. Okay, so if you remember from when we did translations, whenever we translate a shape, all the points move the same distance in the same direction. Okay, so D is going to go to D prime there, and E is going to end up over here. And so we can draw our translated shape. These are our translated points. And let me get a line segment so that I can go ahead and sketch in our translated shape, which I am going to label ABC. ABC. Okay, and then once we get it to this location, then it's easy to see whether you need a rotation, a reflection, or what have you. And here it's very obvious that this is going to be a reflection, right, across a vertical line. So we can make a vertical line here. And we can label that N again. And so then we can describe this operation. Again, we can do that in words or in function notation. Let's start with words. We can say translated the distance and direction F to F prime. And actually we could do that in as a line segment. So let's get the line segment notation and put F, F prime. So that was the first step of our operation here. The second step was to reflect across a vertical line. Reflect across the vertical line N, or rather reflected across the vertical line N. So that's the worded description of this sequence of transformations or sequence of isometries. In function notation, how this would look is capital T for translate, F, F, F prime for our subscript, for the moving this in the distance and direction of F to F prime. Our input shape was FED, and our output shape was ABC, which we labeled ourselves. And then finally, we reflected, so R for reflect, subscript N for the line of reflection that we labeled, and that was ABC for our input points, and our output points were F prime, E prime, D prime. Output points or output shape. Um, so that would be the answer for number 2. And so looking at number 3, um, you can pretty much do that same strategy of translating your shape so that one point is on top of another. So if I was going to do this, I'd probably do it to where Z is on top of Z prime. And then I would say, okay, do I need a reflection or a rotation? And it looks like here it's going to be a rotation. And you just want to make sure that you measure the rotation angle and you specify what point you're rotating about. Same thing here. I would probably translate this to the left so that A is on top of A prime, and then I would see what do I need, a reflection, a rotation, etc. Um, there's going to be multiple answers on how to do this. Translating and then doing that, that's not the only way of getting this shape onto this shape. Um, and so if you can come up with your own unique way of getting this over here using some combination of translations, rotations, reflections, then, that's fine. Uh, in this case, you can actually take this shape into this shape in one um, transformation with a rotation. But if you are going to do that, just make sure that you find your center of rotation. So here, your center of rotation, you'd find it by connecting corresponding points. So actually, in that case, those are not corresponding points. If it was a rotation, in that sense, those would be corresponding points because it got rotated this way. And X corresponding point would be right there. And so you could say that this was a rotation in that direction, but the center point is likely going to be somewhere over here, most likely. But you find that center by making the perpendicular bisectors to this red line segment and then find the perpendicular bisector to this line segment. And then you can confirm that that's the center point by finding the perpendicular bisector to this line segment. So any way you want to do it, like I said, there's multiple answers to these questions. The most important thing is to just be able to visualize how you can take a shape into how you can take a pre-image onto its image through a series of transformations and being able to visualize that in your head. That's really what we're trying to practice here. So anyways, good luck with that. That's all I got for this.